All right, so we're in 3.2 now, and in this section we're looking at nonlinear models. We spent 3.1 looking at applications of DEs that we've already looked at back in section 1.3, but started solving them and using them in problems. Even though it says nonlinear models, plural, we're actually only looking at one nonlinear model in this section, namely the logistic model. If you read through your book, it talks a lot about the logistic model, and then it does another example where it works through a nonlinear model involving chemical reactions. We're not talking about that example in this class. So we're really just focusing on this thing called the logistic model. Now, where does the logistic model come from? Well, the way we're going to introduce it here is as an improvement on our population growth model that we talked about back in 1.3. Here's your population growth model right here. dp dt equals kp. Remember, p is the size of your population, t is time. And when we introduced this, we came up with this by making an assumption about how populations grow. We said that we expect the rate of growth of a population to be directly proportional to the size of that population. In other words, the larger a population grows, the faster it grows. With that assumption, it's fairly easy to see that things get out of control pretty quickly. We talked about this back in 1.3, but if you keep increasing the size of your population, which a positive growth rate will do, then this relationship says that the population will continue growing faster and faster and faster. What that does is it creates an explosion in your population size in a relatively short span of time. And that's easy enough to see if you solve this directly, because the solution is an exponential function. So we would be getting exponential growth in our populations. Now, that might be a reasonable assumption initially, but what happens if your population starts getting too big? Well, a population exists within an ecosystem or an environment, and any population requires certain resources to live: food, water, shelter, etc. A particular environment or ecosystem can only sustain a population up to a certain size, because once a population grows beyond that size, whatever that happens to be, it starts to exhaust its resources, and when that happens, the population is going to start dying off. You're going to lose your growth and start seeing decay in your population. So that upper limit that a population can reach before that catastrophic kind of thing happens is going to vary depending on what the population consists of, what kind of species we're looking at, what the environment looks like. But in any given situation, we're going to think of that as a constant K, which we call the carrying capacity. So a particular population, we're going to assume, cannot grow beyond its carrying capacity of K. Otherwise, bad things start to happen. So what we need to do is take our original model, which has, remember, if this has a solution that's an exponential function, exponential functions have no upper limit. They grow indefinitely. We need to modify this or increase the resolution of this model so that we're not just throwing it out completely. This is a good assumption to start with, but we want to enhance this or refine it so that it takes this additional factor into consideration. So what should that really look like? Well, what we want to have happen is if our population is starting to get close to that carrying capacity, think about this in logical terms, intuitive terms. A population is not just going to skyrocket until it blasts into that carrying capacity and then just come to a screeching halt, right? As the population gets bigger and bigger and starts to approach this value of K, we're going to start seeing the population growth taper off a little bit. It's going to start getting slower, and the closer P gets to K, we're expecting our population growth rate to approach zero. We're approaching it to basically come to a halt. So that implies that if P is getting close to K, we're looking at this assumption down here, then our growth rate is getting closer to zero. It's approximately zero. If P is not anywhere near K, then we're going to assume that the carrying capacity doesn't really have an impact or has a very, very minimal impact on the growth rate of that population, because we haven't really entered the danger zone yet, if you want to think of it in those terms. So in that sense, if P is small enough, let's say that P is close to 0, then we want to assume that this model does the job in predicting the growth rate of our population. And so we would say dp dt is approximately kp if P is far enough away from K, or in other words, if P is close to 0. Now you do need to be careful with this assumption. If P is equal to 1, for example, then your population is not going to grow, right? You don't have enough members of that population to reproduce. So there's that you have to think about that as well. But basically, this is just to say that P is big enough for population growth to happen, but nowhere near K. So let's rethink these. Let's not rethink these, but let's figure out a way to modify our original model in a way that encapsulates these conditions as well. What we're going to do is multiply the kp on the right-hand side by a function of p. That's going to affect how dp dt relates to this right-hand side. What I want f of p to do, I haven't specified what this function looks like. I have certain behavior that I want it to satisfy. I would like for f of p to approach 1 as p approaches 0. Now, why is that? As p approaches 0, this approaching 1 would imply that this entire right-hand side approaches kp, giving me this, right? dp dt is going to become approximately kp as p goes to 0. That's satisfying this first condition. If f of p is going to 0 as p goes to k, that would help satisfy this second condition here. Because again, when p gets close to k, we would like our population growth model to approach 0. If f of p is approaching 0 when that happens, then this entire right-hand side is going to 0, which does what we want it to do. Okay, now this function, f of p, can be an infinite number of different things. There are infinitely many functions that satisfy these two properties, but what we want to do is pick the simplest possible case to work with. So what's the simplest type of function that exists? Well, technically a constant function, but no constant function can satisfy both of these. So what's the next simplest? A linear function. I would like f of p to be a linear function that satisfies both conditions. And the function f of p equals 1 minus p over k does that. You can verify that easily. As p goes to 0, this term goes to 0, which means f of p goes to 1. That's what we wanted it to do. As p goes to k, then this term goes to k over k, which is 1. 1 minus 1 is 0, so f of p is approaching 0. Both of these conditions are met. So I'm going to take this expression and put that in for f of p right there. Okay? In addition, if I assume that my population has an initial size of p naught, then that lets me turn this mathematical model into an IVP, because I have p of 0 equals p naught. So now I have something that I can solve, and that's our next step. To solve this thing, first of all, this model is what we call the logistic model. And you'll see in the homework that even though we defined this thing, or came up with it rather, by thinking about population growth, it turns out that this model applies to a lot of other cases, a lot of other applications as well. So the exercises will help you flesh that out some more. We're only going to consider the population growth case in this video. But let's solve this thing. You may notice that this thing is a separable equation. If I separate variables on this, I'm going to get dp over p times 1 minus p over k equals k dt. Okay, fairly straightforward separation of variables. Now, in order to solve this, I would have to integrate both sides, but this is an integrand that would require partial fractions. I couldn't think of the name. We have to do a partial fraction expansion on this thing. I think I've done one example in this video series where I actually went through the work of doing partial fractions, but in general, you're not going to see me do the work there because that's Calculus 2 stuff. I kind of expect you to fill in those gaps. I would rather get to the point faster. So if you do a partial fraction decomposition on this guy, you can see it's going to become 1 over p plus 1 over k over 1 minus p over k. That's fine. I could leave it in that form if I wanted, but I would prefer that second term to look a little bit simpler. So I can multiply the numerator and denominator by k to cancel these k's out. That gets me 1 over k minus p. This is, if that looks sloppy, I had a typo there that was a minus. It's meant to be a plus. Okay, you'll see another little fix like that on the next page. So using this partial fraction expansion, I can now integrate both sides of this thing up here. That's going to look like this, okay? Now, doing the integration here is fairly straightforward. You should see without too much trouble that you get the natural log of p minus the natural log of k minus p, and on this side we get kt plus c, right? Use some logarithm properties, or a logarithm property, to consolidate these guys, natural log of p over k minus p. Then cancel the natural log by taking e to the power of both sides. And once again, we keep seeing this over and over again, but even though this would technically become e to the kt plus c, or e to the kt times e to the c, we just take that e to the c and continue calling it c and move it out front. Okay, so we've done this enough times to where you should be comfortable with that. Remember, the goal here is to find an explicit solution for p. So this is algebra from here on out. I can multiply both sides by this denominator, k minus p, and after distributing, I'm going to get this. Here's where the k appears, here's where the minus p appears. Then I'm going to add this term over to the left. I'm collecting my p terms, basically. To get from here to here, I would factor a p out of both of these terms and then divide by 1 plus c e to the kt, because that's what would be left. That leaves me with this right here, okay? And technically I could leave it in that form, but I'm seeing a lot of commonality between this term and that term. So what I'm going to do is multiply everything by 1 over c times e to the negative kt. Basically that cancels the c and the e to the kt out, right? E to the negative kt. All right, now this term is going to just leave a k behind. This term is going to go to 1 because I've canceled everything in this term, and notice I've moved that 1 over here. That can be a little confusing because it looks like this one is the same as this one. It's not. This term is becoming 1, and I'm just switching their places. This term should become 1 over c e to the negative kt, but I didn't write that c as 1 over c. And why is that? Well, remember, c is an arbitrary constant, and we actually know that it can't be 0 from where it came from. See if you can figure out why. So its reciprocal is defined, and it's just another arbitrary constant. To keep things simple, I'm going to continue calling it c. Remember, we do that kind of stuff with these constants of integration. So this is where my solution has ended up. Now, there was more to this. Remember, this is an IVP. So we have an initial condition, and the purpose of that initial condition is to get a value for this c right here. So if I were to substitute p of 0 equals p naught, I'm plugging a 0 in for t, which makes this term go to c, and then this becomes p naught, giving me this. I can solve this for c fairly easily. You should see from the algebra that c is going to come out to k minus p naught over p naught. So this thing is what I would be substituting for the c right here. But I don't like the way that looks, so typically what we do instead is we just give this thing a simpler name. I'm going to call it a, which is fairly typical, and that allows me to put an a here in place of that c. We just understand in the background a is equal to this expression. But this becomes the specific solution to my logistic model with that initial condition that we gave. Okay? We're going to use that. But in addition to just solving this DE, there's some more stuff that I can do with the original logistic model that we came up with. If you notice, let's go back to that real quick. Here is my logistic model right here. This is an autonomous differential equation, right? It's autonomous because the variable t makes no appearance. And if you remember back in 1.3, we sort of talked about the fact that most applications that we look at least at this level, you know, at this part of the book that we're in, are going to be autonomous. And in section 2.1, we talked about how we analyze autonomous equations. We look for critical points, we look for equilibrium solutions, and we create phase portraits. I'd like to do that for my logistic model. So that's going to be our first example, is kind of thinking through that. We want to find all equilibrium solutions of the logistic model and create a phase portrait identifying all the critical points as either attractors or repellers. Okay, so here was, once again, our logistic model. dp dt equals kp times 1 minus p over k. Okay? And the first thing that we do is we find critical points. That is, we take this guy and set it equal to 0. K times p times 1 minus p over k equals 0. That implies that p equals 0 from this factor, or this expression equals 0, 1 minus p over k, but it's easy to see that that only happens when p is equal to k, because again, this becomes 1 minus 1, which is 0. So our two equilibrium solutions are p equals 0 or p equals k. Either no population or our population is at our carrying capacity. Okay, so we wanted to create a phase portrait. And I have a 0 here. I'm going to put k. Let's put k. Actually, I want to. No, that's fine. We'll do it right here. That should be okay. K, not p. K. Okay. Now remember, what we want to do is plug in. We want to determine basically what's happening for different sample points in these little intervals right here. In other words, is our dp dt increasing or decreasing? So let's start with a negative value of p. First of all, understand that k is, both of these k's are going to be positive numbers. This k corresponds to the growth rate, so we're going to assume that k is positive here. It's not the growth rate explicitly, but it's related to it. This k right here is uppercase. That's our carrying capacity. And remember, it represents an actual population size, which can only be positive. So that's positive as well. If p is negative, meaning less than 0, then I have a positive times a negative here, and then I'm subtracting a negative from 1. This would have to be positive. So I have negative times positive, which is negative. Okay? So we're going to see decreasing happening there. Now, this kind of doesn't really matter. Even though I can consider p being negative for the purpose of my phase portrait, whoops, I was off the screen there, it's not going to matter because realistically, your population can never be negative in the first place. So as a function, we could say this, but it's irrelevant. We can kind of ignore it. What happens as in between 0 and k? Let's pick a value like k over 2, for example. Okay, or actually, let's not even do that. Let's just think of what a value in between 0 and k would look like, somewhere in this interval. We're looking at a number that is less than k, but still positive. Okay, so plugging that in for the p's here, this p will be positive because we just said that we're plugging a positive number in. If you plug in a number here for p that's smaller than k, then this is a proper fraction, and 1 minus a proper fraction will always be positive. So everything in here is positive. Our phase portrait suggests that our population will be increasing when the population size is anywhere between 0 and k. What happens if we pick a value larger than k? Well, we're still working with a positive number, so if we plug that in for p here, this whole thing is positive. But on this side, if I plug in a number for p that's larger than this k, then this term becomes an improper fraction. It's larger than 1. So 1 minus that would be negative. Positive times negative is negative. Now this captures what we expect to have happen because, excuse me, the population, if it were to be larger than our carrying capacity, then we expect the population to start decreasing in size because we've exceeded that threshold. That can happen, hypothetically, if you take a population of, I don't know, deer or field mice or whatever, and then just move them into an environment that has a lower carrying capacity than the total size of that population, you'll see them start dying off. So we expect our population to decrease once we pass that carrying capacity, but increase if we haven't gotten there yet. So that means 0 is a repeller, and k is an attractor. Okay? What does that mean intuitively speaking? If you have a population, it's going to tend to grow. That means it's going to move away from zero, right? You're expecting your population to move away from zero. That's what it means for zero to be a repeller. You expect your population to grow, but we know that it can't grow past k. So whichever side of k we're on, we're expecting the population size to approach that. And that's what makes k an attractor. Intuitively, our results here make a lot of sense. Okay? So here is what we're looking at graphically speaking if we had a solution curve. Now this, if you your book approaches their derivation of the logistic model differently than how I approached it. My approach is equivalent to the book's approach. You'll get all the same answers in application problems whether you use mine or you use the books. But if you're reading through the book and you're thinking, why does my logistic model here look so much different than Professor Dale's when I derived it in the video? And that's just because of the approach that they chose to take. In my approach, this thing that they're calling A over B here is what we're calling K. That's our carrying capacity. And this A over 2B here is half of that value, K over 2, K over 2, K over 2, okay? And what these three cases are showing here, this K over 2, we're going to see the significance of that in this next example, which I'll probably do in the second video. So don't worry about the K over 2 quite yet. It's showing you what the solution curve will look like depending on where our initial population size is. Notice in cases B and C here, if your initial population is between 0 and K, then your solution curve, your logistic curve, is going to be increasing, right? It's increasing as time passes, but it's also approaching K without ever getting there. So K, as an equilibrium solution, is actually acting as a horizontal asymptote. Same thing with 0. And you see in both this case and this case, 0 is acting as a repeller because the curve is moving away from 0 in both cases. K is acting as an attractor because the curve is approaching K. All right. Now, in the case where your population size actually exceeds your carrying capacity, like we said, you expect your population to start dying off, so it's going to decrease. K is still acting like an attractor in this case. All right. So this is graphically what we're seeing from the phase portrait that we created. We'll continue looking at this example and kind of pick apart the logistic model a little bit more in the next video.